Sampling is a process of taking a time snapshot of an analog entity. In analog to digital converters, for instance, a sample and hold circuit is often used to take the continuous time signal at the input and turning that into a discrete time signal at the output that can then be converted to a digital signal at the leisure of the ADC core before it's transformed into the digital signal processor. In this respect, since the digital signals is almost always discrete time, this sampling is an inherent process in an analog to digital conversion. Another important function of a sampler is to sample, for instance, an offset voltage. In an amplifier with an offset, what one can do is to set the input signal to 0 using a suitable switch, and in doing so you can measure the offset voltage at the output, for instance, somehow sample that, and then subsequently use a circuit to subtract the offset from the input, like so, such that you can amplify the input signal through the amplifier without amplifying the offset as well. This is sometimes used also in ADC cores in order to get better accuracy and more bits. In a CMOS process, the sampling is very easy to do. This is due to the properties of the MOS transistor. One of these properties is that when you turn the transistor off, so in this case here, when you have a clock signal which is low, the transistor goes very high impedance. And that means that you can store a voltage signal on a capacitor simply like that. The other important property of the MOS transistor is that when you turn the transistor on, so when the clock signal here is a high voltage, then the transistor acts as a switch which has a non-resistance but otherwise no voltage difference between the two inputs once the current has stopped flowing. So you turn the transistor on, the input voltage will charge up the sampling capacitor, and once you have reached the same voltage on the sample as at the input, you can turn the transistor off and retain the input sample across the capacitor. To illustrate the process, let's think of a sinusoid-like input signal here and a sampling clock like this. So when the clock is high, the transistor will be conducting and the sample output will be equal to the input. This is also a sample or track and hold circuit, sometimes described as. When the clock goes down, the transistor goes open circuit and the voltage at the output, the sample voltage, remain constant like this. So the sample value is the period where the clock is low. Now, one thing to remember about the sampling here is that in order to turn the MOS transistor on, we must have a gate to source voltage which is larger than the threshold voltage. Now that means that the input voltage here can't be as high as the voltage on the clock, otherwise we won't get the sample at the top end here. So that's the difference between the clock voltage, which is gate voltage, and the input voltage, which is source voltage, needs to be larger than the threshold voltage. Now, another thing that is really important to consider is the finite fall time of the clock. So when the clock goes low, this is when the sample is taken. Now, since the sample is also being taken at the time when the clock input drops below one threshold above the input signal, if there's a slope on the falling edge like that, the time where the sample is taken can be dependent on the input voltage. Now if the input voltage is mid-rail like that, the sample will be taken quite soon after the beginning of the drop of the voltage clock. However, if the input voltage is a fairly low voltage, the sample would be taken at some later stage like that. Now that obviously generates an error in the sampling value. Now, to put this into perspective, let's think of an input voltage which is a sinusoidal signal, and let's assume that we are sampling audio. That is, we have 16-bit resolution and we have a frequency which is 20 kilohertz or lower. Now, since the maximum voltage change is the angular frequency times the amplitude, and since we can allow a voltage error which should be half an LSB, which is the maximum amplitude divided by 2 to the power of 16, or something like that, and then half that value, we can see that the voltage error we get is going to be equal to the maximum dVdt multiplied by the time error in the sampling. So that means that the maximum error we can allow in the sampling time will now be 2 to the power of minus 17 divided by the angular frequency. And if this is audio, this becomes 61 picoseconds. Now this should be a bit sobering because 61 picoseconds is a very, very short time when we're dealing with audio signals which has a fairly low frequency. Now the key take-home message from this is that we need to have a very fast clock or clock edge, and the other point is that we need to have a very stable clock that has very little time jitter. And this is really quite important for any sampling process. Sometimes the input voltage range that is imposed by the sampling, i.e. that the input has to be lower than the clock minus the threshold voltage, is not workable. In that case, what you can do is to add a parallel sampling with a PMOS device, which is turned on at the same time as the NMOS device, i.e. is operated on the inverted clock. And now we have that the input voltage has to be smaller than the clock high voltage minus the end threshold, or that the input has to be larger than the low clock voltage plus the absolute value of the P threshold. So the P transistor will conduct input voltages when the input voltages are quite high, and the N transistor will conduct voltages when the input voltage is quite low. You can also use just a single PMOS transistor in case you have only high voltages on the input. So the clock high and clock low voltages are the voltage between which the clock signals swing. It needs to be emphasized that the body connections for both of the sampling transistors needs to be connected to the appropriate power supply. If, for instance, you were to connect the body of the PMOS transistor to the source, the diode between the drain and the body could be forward biased in some instances. Also, during the sampling process, the source can actually change. If, for instance, the sample voltage is lower than the input voltage when the transistor turns on, then the N transistor source will be on the right hand side. If, on the other hand, the sample voltage before the transistor opens higher than the input voltage, then the source will be on the left hand side. So we might have current flowing from left to right, or we might have current from right to left, depending on the value of the input voltage and the previous sampled value. So this is one example where you cannot actually tell which side of the transistor is the source, because it depends on what the circuit is doing.